So to prove that square root of 2 is irrational by contradiction, let's again take apart the statement of the theorem. X is a number such that x squared is equal to 2 is our premise, our hypothesis, our antecedent, whatever you want to call it. Then, implication, x is not a rational number is our conclusion, our consequent. X is not rational. Okay, so if we're going to prove this by contradiction, what do you want to start? What assumptions do we get to start with?
X is a number such that x squared equals 2 and
Okay.
x is rational.
Great. So we start in a proof by contradiction by assuming that P is true and Q is false. And again, that gives us a lot of information to work with. That's one of the nice things about proofs by contradiction. So we assume that P is true. So assume that x squared is equal to 2. And that Q is false, so that x is a rational number. So there are our set of assumptions. There's not much that we can do with the first one, but the second one we need to expand on. X is rational. How do we plug the definition of rational number into that assumption so that we know what we can say about x in a formally? What does it mean that x is rational? Yeah. Okay. So by definition, this means that x is equal to a ratio, n divided by m. And what can we say about n and m? Okay. So that's one of the things that we can say.
They have to be whole numbers.
Yeah, that's part of the definition of integers. So we can say that n and m are integers. What else can we say?
M can't be 0.
M can't be 0. Okay. Anything else?
They share no common factors.
Okay, right. So the greatest common factor, or the greatest common divisor of n and m is 1. In other words, we can assume, and this is actually something that's not really part of the definition of rational number, but it's an immediate sort of theorem, a consequence of the definition. We can assume that n and m have no factors in common, because if they did, we could factor them out and reduce the fraction into its lowest term. So basically making the lowest terms assumption here. We assume that n and m have no common factors. Okay, so those are all the things that we get from the assumption that Q is false. All right, then where do you want to go from there? What do we do with all this information?
Do P over Q squared equals 2.
Yeah. We have two equations, both of which make a claim upon the identity of x. One of them is that x squared is equal to 2. The other is that x is equal to n over m. So if we want to get somewhere, let's try and get those two things together. So substitute n over m into our equation, which defines x as the square root of 2. And that will give us then, so now here comes our new work. N over m squared is equal to 2. Right? And we can rearrange this equation, squaring both the numerator and denominator, and then multiplying the m squared to both to the other side. N squared is equal to 2m squared. This is the part that we were sort of talking through informally on Monday. Okay, so n squared is equal to 2m squared. What does that mean for us? What kind of mileage can we get out of that assumption? This is where the number theoretic thinking comes in. So if n squared is equal to 2m squared, what does that tell us about n? What kind of a number must n be? Why?
Because it's 2 times m.
Yeah. N must be even because we can see from this equation that n squared must be even. Because according to this equation, it's equal to 2 times another integer, right? It's equal to 2 times m squared. Since n squared equals 2k, for k equals m squared, an integer. Right? Okay, so n squared is even. And therefore, what about n? If the square of a number is even, what does that tell us about the number itself? Yeah. I wouldn't make us prove that statement in this context, because again, in a number theory class, you'd have to prove that, though. How do you know that if the square is even, then the original number is even? It has to do with the fact that 2 is prime. We can't say the same thing about if n squared is a multiple of 4, then n is a multiple of 4. That doesn't work, right? Because 2 squared is a multiple of 4, but 2 is not a multiple of 4. But since 2 is a prime, and divisibility by 2 defines evenness, then we can make this claim. Thus, n is even. But if n is even, that means that n is equal to 2 times something, 2 times L, for some integer L. But then, so what? What can we do with that information? Now that we know something about n, let's go back to our story over here on the left. If n is equal to 2L, then what's n squared? How do I simplify 2L to quantity squared on the left-hand side? Yeah, the 2 gets squared, so we end up with 4L squared. And then dividing both sides of this equation by 2, 2L squared is equal to m squared. Why does that set off my alarm bell? What does that suggest that I can do now? What does it tell us about m?
Doesn't that mean they're essentially the same number, since m can be shown to be even as well?
Ah, right. So, in other words, not the same number, but the very same logic that we applied to n, we can now apply to m as well. Thus, m squared is even. Because it's equal to 2 times L squared, right, for L, an integer. And hence, what about m? M is even. Okay. We are so close to our contradiction. What is the contradiction that's on the board right now? All the elements are there. It's just a matter of putting them together. Yeah.
That since they're both even, they share a common factor.
That's right.
2.
What common factor do any pair of even integers share? 2. By definition of evenness, right? So, we have shown, I'm going to try to highlight these as best I can. We've shown that assuming p to be true and q to be false forces both n and m to be even, but that's a problem because n and m are supposed not to have any common factors besides 1, right? And so because n and m are both even, what we can say, even more to put a finer point on it, this tells us that because 2 is a factor in common, that the greatest common divisor of n and m is at least equal to 2. And so we have a statement here. The statement that n and m share no common factors, whose negation must also be true in this alternate universe. And so typically, how do you like to finish your contradiction proofs? Once you spot the contradiction, what do you usually write? There's like different styles for different mathematicians here. What's your favorite sentence to finish a contradiction proof?
I just like to state the contradiction again. So like,
Okay.
I say like because 2 is a factor in both m and n, this causes a contradiction because the GCD is 1.
Yeah, this contradicts the assumption. Yeah, that's a good practice, to say specifically what is the contradiction at which you arrived. GCD of n and m is equal to 1. And then we can be satisfied with that proof. Sometimes mathematicians, especially if they're from the old school, they like to use words like absurd This is absurd. Therefore, our assumption must be false, and we've proven. Yeah, no, feel free to use the word absurd liberally in contradiction proofs. It's one of those. Absurd is a word that you have to earn in a contradiction proof, but when you earn it, you've earned the right to use it. Because that's exactly what a contradiction proof does. It arrives at a statement which on its face is absurd. And that, therefore, justifies why the original statement that we assumed to be true, namely we assumed our theorem was false, cannot itself be true.